Hi, everyone. Today we're going to be introducing to you Shutter, and we're also going to be showing you how you can build on the platform. Shutter uses advanced cryptography to make your favorite platforms more fair and credibly neutral. It's relevant in a wide range of different applications. One of them is front running and sandwich attacks. If you submit a transaction to an unencrypted mempool, then you're basically exposing your transaction, giving the opportunity for searchers and MEV bots the opportunity to place transactions either before or both before and behind your transaction, thus manipulating the price and essentially stealing money from you. In order to prevent this, we have shielded trading on Gnosis chain. We basically encrypt transactions before they get to the mempool. As a result, the block builder can't see the contents of the transactions and just puts your transaction at the top of the block. After the transactions have been ordered in the block, then it's passed to the validator. They decrypt your transaction and process it as normal. We launched this in July of 2024, and it's been going very well. We have an Explorer, so you can see the real-time status of all your shielded trading transactions. It's also applicable for DAO voting manipulation. If you are a member of a DAO that uses Snapshot in order to conduct votes, you'll notice that the default setting is that every vote is publicly visible immediately after it is cast. But this opens the opportunity for a range of different bad practices, from voter apathy to outright vote manipulation by large voting whales. And so, in order to prevent this, we have shielded voting on Snapshot. Basically, what we do is anytime someone casts their vote, we immediately encrypt it so no one can see how they voted. And then after the voting period has ended, we decrypt all the votes at the same time and reveal the results. This means that everyone has the same information while voting. We launched this in October 2022, and we have protected more than 630 DAOs, and we have encrypted over 300,000 transactions. But Shutter is actually applicable to a wide range of games and consumer dApps as well. And that's what we're going to get into right now. So let's play a game. We'll start off with something super complicated, rock, paper, scissors. I'm sure many of you already know the rules. So basically, there are two players, and there are three different moves: rock, paper, and scissors. So on the count of three, each player reveals their hand at the same time, and rock beats scissors, scissors beats paper, paper beats rock. If there's a tie, you do an instant rematch. So that's all well and good if you're playing for fun, or if you're playing for something low stakes, like riding shotgun in the car on a road trip. But what if you're playing on chain? What if you're playing for a large sum of money? Well, the more sophisticated the technology, the more you start to introduce information asymmetry. And what actually happens is that one person is forced to reveal their move first, and the other person has the opportunity to see their move and then plan their own move accordingly. Obviously, the player who reveals their move first will lose every single time because the player who reveals their move second has the benefit of this information asymmetry. And this relationship is actually the same thing which happens with MEV bots and the mempool and voting whales and voting platforms. So let's fix this game. Well, some people would say let's just introduce a trusted third party. Obviously, that's not a good idea. I think most of us are in crypto because we want to eliminate trusted third parties. So, what Shutter, or the reason why we want to eliminate trusted third parties is because they're prone to all sorts of problems. They may solve one problem, but two more will arise in its place. The first is corruption. Imagine if we're playing a game of rock, paper, scissors for $100 million. One player would have a massive incentive to bribe the trusted third party, even $99 million, in order to leak the opponent's move so they could plan accordingly. They would take home $1 million in profit. Also, the trusted third party would be really tempted to take that bribe of $99 million. And of course, trusted third parties are often in a place to extract value over time. And the more value that they extract, the more powerful they become. And the more powerful they become, the more entrenched in their position. More entrenched in their position, the more value they're able to extract. So you can see that this is a downward cycle of entrenchment and centralization. So what Shutter does as an alternative is we introduce a credibly neutral third party. And here's how we do that. We utilize something called a commit and reveal scheme. And in order to generate the encryption and decryption keys, which are needed for commitments and reveals, we use a decentralized keeper set. And specifically, we use a form of multi-party computation called threshold encryption. So we assume that there is an honest majority within this decentralized keeper set because we need X of n keepers in order to collaborate or collude to generate a decryption key. Of course, we're not just leaving it to trust. We also have other mechanisms to prevent collusion. One of them is snitching so that keepers can tattletale on one another. And of course, there are economic incentives like staking and slashing. So in the case of rock, paper, scissors, here's the way that Shutter as a commit and reveal scheme would work. Each user would submit their move, and as soon as the user submits their move, the user and the keepers would work together to encrypt that move. After both players have submitted their encrypted moves, the round ends, and then the platform itself and the keepers work together to decrypt both moves at the same time. At that point, the winner is revealed. Pretty simple. So let's build a game. One of the perfect opportunities for Shutter is imperfect knowledge games or simultaneous move games. And there are a wide range of games in these categories. Of course, rock, paper, scissors is a perfect example, but so is the very well-known Prisoner's Dilemma. There's also the famous board game Diplomacy, as well as more avant-garde games like Cards Against Humanity and Secret Hitler. So you can take any one of these games and actually turn it into an encrypted game using Shutter and our commit and reveal scheme. You can also use a bunch of consumer dApps or build a consumer dApp. And my favorite use case here are salary negotiations. So if you think about when you're negotiating for salary, someone, either the employee or the employer, has to provide their salary expectations first, and that can give the other party more power. So having both parties reveal their salary preferences at the same time is a super powerful tool for both parties. Similarly, in business, having blind bounties and RFPs or request for proposals can make sure that the procurement process for a company or a DAO is fair and transparent. You can also use it for a lot of consumer dApps which feel like games. So you could have a donation auction where all of the donations are encrypted until the auction end, and then the highest donation gets a particular prize. You can also use commit and reveal for non-games, something simple like a time lock gift. Maybe you want to give a gift on chain, but only have it be delivered on a particular date, i.e., someone's birthday or maybe a holiday. So, this has been a brief introduction to Shutter and how it uses advanced cryptography to make your favorite platforms more fair and credibly neutral. If you are developing a platform, get in touch with us and we would love to show you how to integrate. If you are a user, you can start using Shutter today in order to protect yourself against MEV bots on Gnosis chain with shielded trading, or against vote manipulation on Snapshot with shielded voting. And if you're a builder here at the hackathon, you can start building on Shutter today. And we've got some wonderful tools and developer docs to help you go from zero to building a prototype in just 48 hours. I'm going to hand it over to my colleagues. They'll show you how to do exactly that. Thanks so much.
NanoShutter repository. This is just a simple implementation for Shutter network, uh, which is specifically designed for educational purposes. Do not use it for production-based systems. This has APIs which are time-based, which are used for time-based encryption and decryption, or custom epoch or message-based encryption and decryption. The APIs are as follows. There's a encrypt with time, which encrypts the message for future decryption. So whatever timestamp of future you send in the request body, it will be decrypted after that. To decrypt the same message, we can use the decrypt with time. Now for custom epoch-based encryption, you can send the epoch ID or custom message in this API, encrypt custom, and the same can be decrypted using decrypt custom. Now the whole API system is deployed and can be accessed through nanoshutter.staging.shutter.network. And if you want to deploy it on your local, then you can use our Dockerized setup, or you can directly run the Go server. How to use these APIs? For time-based encryption, you can send a request body. In that, you can send a ciphertext message, which would be the secret message to be encrypted. With that, a future timestamp, after which this should be decrypted. In response, you'll get the encrypted hex string. To decrypt this message, after the time is elapsed, you can send the encrypted hex string and the timestamp for which it was encrypted, and you'll get the response as the secret message. Now, for custom epoch-based encryption, this is not based on time or anything. You just have to pass the correct epoch ID. So the same epoch ID needs to be passed for encryption and for decryption, and the ciphertext would be the custom epoch secret message, and you'll get a encrypted hex string. And for decryption, you'll just pass the encrypted hex string, you'll get the secret message back. Now let's try it out. So we'll try to encrypt ABC ciphertext for the current timestamp, and this gives us an encrypted hex string. Now this can be decrypted for the same timestamp. This is same, and we get the message back. That's pretty much it, guys. Happy coding.